So folks, we're going to dive a little bit into Taylor series today. We're going to talk about a couple things that we do. And the first thing we're going to talk about is how we can represent a Taylor series. Now, what we did yesterday and when we were working in classes, we had sine of x. And what we did with sine of x, we had this function sine of x. And we had it centered at x equals 0, right? We were talking about it centered at x equals 0. And the Taylor series that we came up with looked something like this. And I hope that I'm not making a mistake. But I think this is the right one. If you remember, you may have learned before that Taylor series, that the sine of x is odd, right? Remember how you learned the sine of x was odd? Well, look at all those exponents, right? So you remember that sine of x was odd and the cos of x was even? Well, that's a nice clue that might help you because sine of x has all the odd exponents. So this is a great way we can represent it. We know this goes on forever, right? It goes on forever. And we could say to ourselves, well, how would we represent this, right? Well, what's a nice way of representing it so that if I plugged in any value of n, I would get, the right expression? This one's kind of challenging. So why don't we start off with something a little easier first? Why don't we start off with something that we've done before, right? Like spin like e to the x, because we started off with this one when we were working on this yesterday. And this one's that's much easier at least. It's much easier for us to wrap our heads around. So my question for you, and why don't you think about this for a second, is if I wanted to kind of plug in any n here, any n, what is an expression that I could use for any n? Remember, when we're doing these Taylor series, remember that we're starting at 0, right? Our first term always starts at 0. So given that we start at 0, what could we write in here for any n? So hit the pause button real quick and tell me if you can figure it out. So if you think about this being the 0th term, and this being the first term, and this being the pattern really starts to emerge here. But once you hit 2, you'll see that, okay, yeah, the general term for this, right, the term that you could kind of plug in at any time is just this, right? And so we call this the general term because it works for any n that you plug in. And usually if you write this as an infinite sum, you're going to write this with the general term. So that's what e to the x equals, right? And so the general term is an important thing that kind of lets you know what you're actually going to be writing if you wanted to represent any term in the series. So now we're going to try something a little bit more challenging, right? This one's going to be a little harder. Because, again, let's think about this. Now we have n equals 0, n equals 1, n equals 2, n equals 3. So what could we write here to make this a general term? Hit pause again. Tell me what you think. Okay, so hopefully we're back after hitting pause, and we've thought about the fact that we need to somehow represent these 3's, right, and the 5 and the 7 as a function of the 1, the 2, and the 3. Hopefully it's not too challenging for us to see that, well, that's just, it's going up by 2 every time, and it's kind of 1 more than double. So hopefully it's not too challenging for us to see this is the general term. Yay. But I left space here for a reason, right? Well, look, I left space because we have this little thing going on here where it's going positive to negative, positive to negative. So we have some -1 action going on, right? And -1 is involved. But the question is, what's happening? Well, when n equals 0, it's positive. When n equals 1, the term is negative. So we want to make sure that when the term is odd, right, it actually turns out to be negative. So I think we just can do this, right? I think it's going to work. That's great, and that is the general term for sine of x centered at x equals 0. So you're going to take a stab at this now. This one keeps going. I guess I should put the factorial there. Okay, so take a stab at that one, folks. Hit the pause button. This is what I'm getting. Don't know if you got this as well. So now when I plug in 0, I need positive. When I plug in 1, I need negative. I think I can use the same thing. So these are all Taylor series centered at 0. And these all have a special name. And I may have mentioned it a little bit during last class, but Taylor series that are centered at 0, where x equals 0, have another name. And those other name are called Maclaurin series. So all 3 of these are called Maclaurin series. And I may be pronouncing Maclaurin like it's a Scottish name I'm not going to be speaking about the Scaltus action for the whole time. But no, Maclaurin series are just those that are centered, or Taylor series that are centered at 0, right? And because they are so common, we actually use Maclaurin series more than we use like non-Maclaurin Taylor series. Like we do more series that are centered at 0 than any others. Okay. So this is just an introduction to the general term. You will be asked for the general term in times. And when you're asked for the general term, that's what you need to supply. Kind of what you would plug in n for. You could also rewrite this, right? If you plugged in n, making sure you could represent every one of the terms. So these are 3 of the Maclaurin series that are good to know. They're good to have in the back of your mind. Like these are series that, in general, you want to be able to kind of think of quickly, and knowing that cos is even and sine of odd maybe help you remember some of these. But these are things that I like to have at the forefront of my mind when I'm dealing with Taylor series and Maclaurin series. So now we are going to make sure that we can do Taylor series that aren't centered at 0, because we have to have that in our repertoire as well. So this is one that is going to be f of x equals e to the negative 2x. That kind of just upped the difficulty on us. And a equals 3. So we're now centered at 3. We are no longer centered at 0 for the first time in a while. So we're going to do the same thing. We're going to kind of figure out this, and we're not only going to figure out the first 3 terms, but we're going to figure out the general term as well. So first thing we have to do is figure out this function. And the question you may ask is, well, how many do I have to do before I start to see the pattern? And the fact of the matter is, you have to do as many as you need to do until you start to see the pattern. And this is already feeling like it's going to be a lot of work. I feel like I may have upped the difficulty more than I wanted to, but that's okay. We'll figure things out on this one together, this row together. Okay. So now we have to figure out this at 3, right? Because now where we are centered is 3. When we write this out, I mean, we kind of start thinking about this. This Taylor series is now the nth derivative at 3. So they're the terms that we're going to have to be writing out. So we're going to have to evaluate all these at 3. So therefore, we're going to need f of 3 at e to the negative 6. And then f prime of 3 is going to be negative 2 e to the negative 6. And then f double prime of 3 is 4 e to the negative 6. Wow. Well, I hope this is enough for us to recognize the pattern. And sometimes you have to do more, because especially if you have some zeros in here, like you do with coses and sines, sometimes you have to do more derivatives till you start seeing the pattern. So let's start writing these out, right? And you know, this is not a bad thing for you to do, folks. If you want to think of it like this, as like a first step, this sometimes helps, and it doesn't always help. It's not like some of you are going to say this is a waste of time, but when you're trying to recognize a pattern, sometimes it helps us start seeing some stuff. So we can come in here and we're going to put the f of 3 here. And f of 3, as we calculate over there, is e to the negative 6. This is negative 2 e to the negative 6. This is 4 e to the negative 6. This is negative 8 e to the negative 6. I think I'm starting to see a pattern already. I don't know if you folks are. Maybe you want to write out the 4th if you wanted to, but we can start seeing what's kind of happening here, right? So if we had to write this general term out, we can break it down to its pieces, right? You know, there's pieces here. There's the factorial piece. There's this e to the negative 6 piece. There's this x minus 3 piece, and then there's this like negative 2 that keeps on coming its way, right? So let's break it down to those pieces. This general term is going to have in the bottom, I think it's just going to have the end in factorial. So we can just leave that here. And we can just have this x minus 3 to the n. I think that's true, right, for all of them. So for the general term, that's going to be true. But now we have to think about these other parts. And this e to the negative 6 seems to be kind of persistent, right? We could put e to the 6 down here if we wanted to, because we could just pop it down. And it's never really good to have negative exponents in the numerator, but you know, I'm going to leave it there just so we can see it nice and clean. Like if you were writing this out formally, in fact, I'll do that in a second, you'd probably put in the denominator. And then we have to figure out this 2 thing that's going on. And I think all that's really happening is we're just multiplying -2 to the n every time. I think that's the general term, folks. So I think we could say that e to the -2x centered at x equals 3 would look like this. And then I will there we go. So this is just this would be the general form. So you could be asked at any time to write the general term out. And if I ever ask you, hey, write the Taylor series out for some function centered at some number, 3 or 4 or 5 or whatever it is, you just have to recognize that means that it's centered at 3, and this is what it will be as long as and this is true for as long as it's going to be converging, and we know e to the x functions always converge. So I'm going to stop this for now, and we're going to come back and we're going to talk about some more things we can do with these series. That'll be in part 2 of this lesson.